Alright, what up, and welcome to today's lesson summary. So today I'm going to be giving an introduction to circular arrangement, which is a subtopic of combinatorics. And this is something we do in year 11, just for some background information. So a little bit about myself. Welcome to Maths and Science with Danuga. This is something that I do as part of the Danuga Marnage mentoring channel, where I'm a maths and science and study skills tutor from kindergarten through to year 11, so I can help you in becoming the most productive version of yourself when you study and providing specific and in-depth detailed lesson lectures for maths and science in kindergarten through to year 11. So come excel in maths and science using my personal guidance. My contact information is right here, and it'll also be in the description of the YouTube video, so go and look at that if you want some personal tutoring. And this free video is a summary of a full lesson I've given to one of my students. So if you want similar personalized coaching from me, then contact me and we can discuss a route of tutoring. Alright, so I'm going to explain the difference between circular arrangement and linear arrangement. So if I give you a question where you need to arrange 5 marbles, black, red, green, purple and orange, into different orders, how many ways of doing that are possible? And you'll tell me if you know how to do linear arrangement. If there's 5 distinct objects, there's going to be 5 factorial arrangements of that. So I think 5 factorial is about 120. 120, I think, but there's 120 different arrangements of this. And what I've provided over here is, where's the laser? So what I've provided over here is 5 examples of arrangements of linear arrangements. And what I want you to consider is, as you can see, these are all different linear arrangements. But if we were to put these marbles and make a bracelet with them, so we connect, this end and this end here, what we come to find is that every single one of these 5 arrangements go black, red, green, purple, orange, black, red, green, purple, orange, black, red, green, purple, and it's all the same. It's just it's like you get the same bracelet, but you rotate each marble, so you just spin the bracelet. It's still the same bracelet. So obviously, when we're going from linear arrangements to circular arrangements, we do tend to overcount some possibilities. So then the question is, how do you actually count the true number of circular arrangements, not linear arrangements? Because so far we know that there is a clear difference between the number of circular arrangements and the number of linear arrangements. So how do we go from linear arrangements to circular arrangements? So what we do is using the general strategy for finding linear arrangements. So what the general strategy is for listing circular arrangements is we get our 5 marbles, we make our bracelet outline, and we typically, how it works in a linear arrangement is there's something called the first position, second position, third, fourth and fifth. So we can do the same ish. I'll explain why it's ish, but we do the same ish 1, 2, 3, 4 and 5, and we just, these are the positions. Now what I do, right, is, so what I do is I get one of my marbles and I fix it in a position like this. So I fix my red marble in the first position. And the reason that I fix my red marble in the first position is that so the reason that I fix this in the first position is because now the whole point of a circular arrangement is that we consider the position of objects in relative to each other. So by fixing this red one here, then it means that we then lose every arrangement where it's the exact same arrangement but just twist it around, because we fix red at the first position. So now we can treat the remaining 4 like a line. So this right here is just a line. So from 2 to 5 it's a line. So 2, 3, 4, 5, it's 4 objects. So it's going to be 4 factorial. So what we do is we just got 4 factorial. And this is the number of ways of listing 5 objects in a circle And 5 factorial is the way of listing 5 objects in a line. And the reason that it is like this is because if we look here, this 5 arrangements, these 5 separate linear arrangements are the same circular arrangement. So for every 5 linear arrangement, there's 1 circular arrangement. So it makes sense why we divide by 5, because 5 factorial divided by 5 is 4 factorial. And the same pattern works for n cases, which is a question I'll actually do for you. So this is the general strategy for finding the number of circular arrangements. You just fix one object. It doesn't matter which object, just fix one object and then treat the rest of it like a line. And now here are some hacks and strategies for solving some of our harder questions. So the first one is to use a simple example. So there are some questions where it might be like, find the number of ways in which you can put n objects into a circle. Now if you don't know how to do it off the jump, you can actually, instead of n, you just do 5 or 4, you figure out the answer, and by doing that you figure out the internal mechanics of the problem, you see what's happening, and then using what you learned from the more specific and easy case, you then expand that into the general case or the harder case. That is one thing. Another thing is the complement method, and the complement method works in questions like this. If I say list 5 objects A, B, C, D, and E such that, or like obviously in a circle, such that A and B cannot be next to each other, how can we do that? Well, we can do like separate cases where it's A and B are separated by 1 object, then A and B separated by 2, then A and B separated by 3, but that's going to take a lot of effort. But what we can do is we go total number of circular arrangements with A and B with no restriction, and then where A and B are together, subtracting those two, we get where A and B aren't together. That's the complement method. And then the last one is separate the question into multiple steps. And this is in the more nuanced problems where, for example, we have 6 objects, we need to arrange them so 3 of them are together. How do you do it like that? We split the question into into like a certain number of steps, where these steps are actually easier than the full question. So that's how we do it like that. So I'm gonna then show some questions, and we can use these strategies here to solve these questions. Alright, so now I'm gonna show you how we do this question here. So start with 10a. How many ways can n people be seated at a circular table if there's no restrictions? So immediately we see it's n people. Now it's very hard for our brain to visualize n people because n is any number. So like obviously our brain likes to visualize a particular number. So what we can do is we can use this strategy here, which is use a simple example strategy. And I'm going to say instead of n, we'll start off by 5, figure out the mechanics of the question, and then apply it back to n. So if there's 5 people in a circular arrangement, then we have a circle, we put person 1 here, we fix person 1, then we have, these 4 positions for person 2, 3, 4, and 5. So that's going to be 4 people now. So if I just put in purple to illustrate that, these are the remaining people after we allocate 1. There's 4 people and 4 positions, so it's 4 factorial. So the answer when there's 5 people in a circle is 4 factorial. Now what we do is, using this, we do the case for n. So if there's n, we put the first person here. Now we figure out how many spots are remaining. Well, the number of spots equal number of people, right? And well, some questions actually the number of spots is not equal to the number of people. That's a more nuanced example, which if you want, I can do a video on that, but it's not going to be in this video. But we see if there's n people and we take away 1. Now there's n minus 1 people. So put this into a circle, it's n minus 1 factorial. So the answer to 10a is n minus 1 factorial. And this is a successful usage of the use a simple example method. Now what I'm going to do is I'm going to erase this question, so you can obviously rewind if you need to relook at it. But now I'm going to look at how many ways when there's, so 10b. So 10b is 2 people must sit together. So again, we're going to start off with the simple case of 5 people. So 5 people, A, B, C, D, and E. So with these 5 people, 2 people must sit next to each other. So the question means that 2 specific people, so we can represent as A and B. So person A and person B have to sit next to each other. So how this works is we put a circle like this, and what we can actually do is, since A and B are the same or have to be next to each other, we can consider A and B as just one really big person that contains 2 people. So now we're going to call this person F. So now we have person F, person C, person D, and person E. So we have 4 people, right? From question A, we know if there are 4 people sitting, or if there are n people sitting in a circle, it's n minus 1. So if there's 5 people where 2 have to be together, then there's 4 groups of people, because we group 2 people together and keep the other one in their own individual group. So there's 4 groups, so it's going to be 3 factorial. However, within A and B, so within this A and B group here, it can actually be A or B or A. There's the different arrangements within that group itself. So how many ways within this group can you list the 2 people? As well, it's going to be 2 factorial, because there's 2 people and 2 positions, so it's 2 factorial. So overall, there's going to be 3 factorial times 2 factorial, and that's going to be the number of arrangements where 2 people must sit together. And one quick thing we can check is, obviously we know the number of ways people can sit with no restrictions should be much larger than the number of ways where there are restrictions. So the number of people sitting in restrictions, when there's 5 people, it's 4 factorial, so 4 times 3 times 2 times 1. And in this case here, it's going to be 3 times 2 times 1 times 2. So in the first one, it's 4 times 3 times 2 times 1. In this one, it's 2 times 3 times 2 times. So obviously this top one is bigger, and this makes sense. Now the question is, instead of 5 people, it's n people. So also, by the way, this thing here where I've put it into 2 different multiplications for the outside group and the inside group, that's an example of the separate into multiple steps method. Because when we're separating into multiple steps, we first arrange the total number of groups and then arrange the subgroups within the groups. So this is how we use this third strategy here. So now we need to use the first strategy where we use a simple example of 5 and then go into the n case. So for 10b, instead of 5 people, it's going to be n people now. So how we do it, and now because we understand the problem, I'm not going to bother drawing a diagram. If you want to, you can. But we have n people, and 2 of them have to be next to each other. So it's going to be n minus 1 groups. So if we have n minus 1 groups, and we want to put n minus 1 groups into a circle, there's going to be n minus 1 minus 1 factorial. And this is because when you get the n minus 1, you fix one person. So now there's n minus 2 remaining, and you treat it like a line. So it's n minus 2 factorial. So it's just going to be n minus 2 factorial. However, since you picked out 2 people, these 2 people can be arranged in different ways among themselves, right? So this first step here, we arrange the groups. Now this step here, we're going to arrange the subgroups. So there's only one subgroup, which is just this, person 1 and person 2 group. So that's going to be 2 people, so 2 factorial. So then the answer to 10b is going to be n minus 2 times 2 factorial. That's our answer to 10b. Keep in mind, if you see any mistakes I make, then put it in the comments and I'll fix the video. But, me and my student both solved these same questions and we came to this answer. So I don't think they're incorrect, but if there is something that's slightly off, just let me know and I'll fix that. So now we're going to be 2 people must sit apart. Now, if you can use some foresight, you can see that this is going to be where we use the complement method, right? And we're also going to be using the answers from 10a and 10b and using that to get 10c. So 10c. What we can actually understand is that with the number of arrangements where 2 people must sit apart is going to be equal. So So the number of arrangements where 2 people must sit apart equals total number of arrangements minus the number of 2 people together. And if you think clearly here, you'll see that this is actually just 10A and this is 10B. So our answer to 10C is just 10A minus 10B. This is a common thing. We got A, B, C equations. We need to use previous parts to solve this. So from 10A, when there's no restrictions, it's going to be n minus 1 factorial. And when there's 2 together, it's going to be n minus 2 factorial times 2 factorial. And this is going to be the answer to 10C. Just, this right here is the answer to 10C. Now the last question is 4 people must sit together. So 10D. Now, for the sake of being specific, what I'm going to do is I'm going to do another simple example with a specific number of people, and then we're going to apply that to the general case. So imagine we have 6 people, A, B, C, D, E, and F. And 4 particular people must sit next to each other. The 4 particular people are going to be A, B, C, and D. A, B, C, and D must sit next to each other. So how many groups are there? Well, this is considered one group. This guy here is 2 groups, and this guy here is the 3rd group. So there's 3 groups overall. So it's going to be, and remember, we fix one group. So we'll just fix one group at the top, and then the remaining we can have 2 factorial. So it's going to be 2 factorial. But within group 1, we need to arrange the subgroups. So how we do this is by saying, okay, there are 4 people. How many ways can these 4 people be arranged? It's just 4 factorial. So this is the answer when there's 6 people. Now let's use what we learned and apply it to the n case. So as you can see, if we have 6 people, we end up with 3 groups. If we have 7 people, 1, 2, 3, 4, 5, 6, 7, we group these 4. Group 1, group 2, 3, and 4. So as you can see, if there's a certain number of people, when you make 4 go together, the number of groups is just that number subtracted by 3. So if there's n people, n minus 3 groups, so arranging the number of groups is going to be n minus 4 factorial, and then arranging the 4 people within the subgroup is going to be 4 factorial. And this makes sense. If we think back to the example of 6 people, we put 6 into n here. So, we put 6 right here. And if we subtract it by 4, we get 2 factorial. 2 factorial times 4 factorial, which is what I have here. So this is how we do this first question here. It's a bit of an easy question, but this encompasses pretty much every topic we do in circular arrangement. So if there is one important question to deeply analyze, it's going to be this one. So rewind back and rewatch this bit if you haven't fully digested it, because it's not going to be worth missing out on. Okay, now on to our second question. A group of men and women are seated at a circular table where there's one more woman than man, and it's asking how many arrangements are possible if no 2 men are sitting next to each other. So before we jump into writing out the combinatorial chain of multiplication, we'll first look at the question and analyze the English behind it and put it into mathematical context. So the first takeaway here is it says there's men and women. So this is quite important, that because the question didn't say blue marbles and red marbles, it says men and women. And what that means is that obviously one person is not the same as another person, right? Each person is their own individual person. So we can conclude that we're dealing with distinct objects here. And obviously, people aren't objects, but this is maths, you know what I mean? We're dealing with distinct, separate things. So the point or the meaning of that is that, for example, if person A and person B are sitting in this order, person B and person A sitting in this order, this is 2 different, even though A and B could be both males in this question, male A and male B is different to male B and male A, where, for example, red marble, and then red marble, still red marbles, right? So we have distinct objects. So in this case, this is, two different permutations, but this here is just one permutation. So that's an important takeaway. Distinct objects. The second one is that there are one more woman than man, and it doesn't specify how many they are. So we are dealing with an ambiguous, case where we let, pronumerals equal to what we want. So we have, I'm going to say n men and n plus 1 women. And it says no two men can sit next to each other. So now we have all the key takeaways from the question. We need to figure out, let's write this down, man, big X, we can't have two men. So now we have all the distinct takeaways from the question. We need to solve it. So how I'm going to solve it is we have this n plus 1 women here. I'm going to separate this group into two subgroups. It's going to contain, the first group contains n women, and the second group contains 1 woman. Now we have 3 groups overall we're putting around this circle. We have group 1, group 2, and group 3. Because we're fitting n men, n women, and 1 extra woman all around this circular table. So we need to first pick, I'm going to start off by arranging groups 2 and 3 and putting them around the circle. And you'll see why I chose to put these 2 groups around the circle first. So if we have an equal number of men and women, and no 2 men can sit next to each other in the circle, we have to understand the only way that this can exist is if it goes in a male, female order like that. So you have men, woman, men, let's put like woman, men, woman, men. I'm trying to make sure we have equal number of men and women. I'll actually just change the color of the women to make it a bit easier to grasp. Color, I'm just gonna make it white. So we have the men and the women like this. So now the question begs us, how do we fit the n men into these groups? Well, we are going to first use the general strategy where we fix one object and treat the rest like a line. So, and by the way, some of you may have the question, you've put men in this like plus type pattern and women in this X type pattern, but what about the patterns where there's women sitting here and men sitting here and this is alternating? Well, these also are valid patterns, but we have to understand they're just like a circular shift from this one here. So we can put men in these positions and women in the alternate ones, or we could put where the men are, we could put the women there. It doesn't matter. We just have to pick one and be consistent with that. So we have a circle, we have to fix one of them. So I'm going to get one man and fix him here. So I'm fixing this man here. Right? Now the rest of this, I'm going to treat like a line. So we fix one man. So we have 3 men left. And how many available spots for men? Men is green. 1, 2, 3. We have 3 men left and 3 spots left. So it's going to be 3 factorial, right? Because it's a line now. And the woman, there are 4 women left and 4 spots for women. It's going to be 4 factorial. And by the way, I've used 4 and 3 because I'm using the strategy of using a simple example. So we're going to then use this and go back to the question afterwards, right? So 3 factorial times 4 factorial is the way in which we organize 4 women and 4 men around a circle so that no men are sitting next to each other. We almost finished the question, but we need to allocate this woman, right? And how we allocate her is we think she can go anywhere in the circle that won't cause 2 men to sit next to each other. So first we look at, because it's a circle and there are 8 people, if you are familiar with how circular fences work, if there's 8 fence posts in a circular arrangement, then there are 8 gaps between the fence posts. So there are 8 positions for this woman to go in. So where can she go in? Could she go in this position? Yes, she can, because she'll still separate the man. Can she go here? Yep. So this woman can go anywhere in the circle without forcing two men to sit next to each other. So it's just going to be, she has 8 positions to choose from, so it's just times by 8. And this is the ways of listing 4 men and 4 women. But the questions ask, 4 men and 5 women. But the question's asking us for n men and n plus 1 women. So how we do this is, now we understand what's happening in the question. We say we're going to 2 groups of n women and n men. So there's going to be, we fix 1 man, so it's going to be n minus 1 factorial now for the men, times n factorial for the women. And then now we've arranged n men and n women, so there's 2 n people overall, there's 2 n gaps, so there's 2 n spots for the final woman to go in, so it's times by 2n. And this is my final answer for this question. I'm fairly sure this is correct. If not, put it in the comments and I will amend it, but this is a very unlikely event that this is wrong. But always check yourself before checking my answer. So this is how I solved this question, using the strategies here and here. Okay, on to our third and final question for this lesson. And in this question we have to derive the formula for a number of circular arrangements of k distinct objects chosen from n distinct objects. So what this means is we have a collection of n objects. From this collection of n objects, we get this subset which contains k objects. We pull this out and we put this into a circle. So this is a very good question that tests if we're able to separate the question into multiple steps. So what we have to understand is there are 2 steps here. The first step is choosing k from n distinct objects. The second step is putting k objects into a circle. So now we're going to see if we can use the multiplication principle, which is something you should be familiar with. I mean, we've used it in the previous question, so if you don't know that, then you should brush up that definitely. Without this, you can't do any combinatorics questions. We're going to use the multiplication principle to combine these 2 steps to get a final answer. So from n distinct objects, and this is very important, we have n distinct objects here. If it said from n people we choose k people, this is the same thing as distinct, because keep in mind, for common terminology, if it's people, it's always distinct people unless otherwise stated. And if it's like marbles, then it's always indistinct unless otherwise stated. So keep an eye out for that. And if you're unsure in a test, then ask the teacher, obviously, because he's not going to gatekeep from you for no reason. You need to know this information. So, but otherwise, it is easiest and best when it literally says if it is distinct or not. In a later video, I'll be explaining how to deal with indistinct objects in a circular thing, because just for some side note, usually in a line, how we remove the overcounting for the same object, or for identical objects, is we just, if you have 4 objects, let's say we have 4 objects and there's 2 A's and 2 B's, where the A's are identical and the B's are identical. How we do it, we go 4 factorial for the 4 objects, and then there's 2 repeating A's, so 2 factorial, and 2 repeating B's, 2 factorial. The thing is, this rule here does not work when it comes to a circle. Even if we fix one person and treat the rest like a circle, we still can't use this right here. And in a later video, I will be explaining why. But for now, we're just going to be dealing with distinct objects, and this makes our life much easier. So the first part, choosing k from n objects. So this is extremely easy. This is just straight one calculation. We go from n, choose k, nck, right? From 8, you got 8c4. This is going to be, I'm not sure off my head, but it's you can use it with the you can figure it out by using the Pythagoras triangle. Is it the Pythagoras triangle? This one here, I don't know, but in this one here, this is going to be 4c1 is this, or 4c2 is this, 4c3 is this, right? But we can just put into our calculator, we have nck. This is from n we choose k, and the other one is putting k objects into a circle. How we do that is we have k objects, so we fix one object, we fix the one object, now we have k minus 1 left. We put the k minus 1 into a circular line, but the line is going to be k minus 1 factorial. So our full answer is nck times k minus 1 factorial. This is the full question, and this is a super simple question if you understand this step right here. But if you don't understand this step, this is basically impossible. So it's really important that we understand these 5 principles of circular arrangement. Pay attention to these, figure out exactly what it means. If you have any questions about these, like text me, email me, comment under the video. I prefer if you comment under the video because then I can see it easier, but do it like that, and that way when your test comes you have a full thorough understanding of everything that happens inside the circular arrangement stuff. So anyway, this is the final answer. So this concludes the video. We've covered how to solve them with the overall general strategy and then our more specific complex strategies. And I've done 3 questions here, which I've handpicked these 3 questions because they incorporate all of the strategies I've taught you. So with this in mind, you should be able to answer 80% of combinatorial questions involving circular arrangement. The other 20% would be words like indistinct objects, and we need to arrange for that. But that is typically a harder topic, and I can't remember covering that in my year 11. So yeah, thanks for tuning in. Hit me up under my contact information for personal guidance, and yeah, thanks for tuning into the video, guys.